Welcome. My name is Stephanie and I'm presenting to you today from the Department of Chemistry at the University of Alberta. And today I'd like to share with you a little bit about the photoreactivity of atmospheric dust and how we can quantify hydroxyl radical production from that dust using molecular probes. We are interested in doing this because there are billions of tons of dust emitted into the atmosphere every year. Now these provide a large reactive surface for heterogeneous reactions to occur on. They affect our climate and they affect human health. Now we know that certain components of dust, such as TiO2, are photoactive, meaning that upon illumination they produce radical species. We are interested in quantifying the hydroxyl radical production, which in this study we use as a proxy for dust reactivity, meaning the more hydroxyl radicals we produce, the more reactive a dust is. Now, the molecular probe technique is a very simple technique that allows us to combine a probe molecule with our dust, which can then be illuminated. And as the dust is illuminated and it produces these hydroxyl radicals, they can react with this molecule that can then form a product which we can detect spectroscopically and therefore quantify the hydroxyl radicals that we are producing. To do this, we use three different dust samples. So we use Arizona test dust, or ATD, which is a common lab proxy for dust. We also use Niger sand, which is a large source sand, or we use Saharan Desert Cape Verde dust, or SDCB dust, which is a depositional dust from the Saharan Desert where it has been transported to Cape Verde and collected. Now, initially we started using coumarin as a molecular probe. Now, coumarin with the hydroxyl radical forms a highly fluorescent umbelliferone, which we saw some very interesting pH dependencies with. So the lower we dropped our pH, the more acidic we made our solution, the more reactive dust became. But unfortunately, our umbelliferone decomposed with light. So the longer we illuminated, the less umbelliferone we saw, and we started to see some funky results. So this wasn't great for molecular probes, so we decided to look specifically at the decomposition of umbelliferone since it is accelerated by hydroxyl radicals. So we saw this result with our SDCB. So when that was in solution with the umbelliferone, it degraded much faster than just by itself. Now, this result was not matched with the Niger sand because it is a larger, less reactive dust. So we didn't see that same decomposition. It was very similar to the background photolysis, which wasn't good because we weren't able to distinguish the two. So we decided to move on to benzoic acid as a probe molecule. So with the hydroxyl radical, it forms salicylic acid, which can be quantified via fluorescence. It also forms two other isomers, but we disregarded those and focused only on salicylic acid. Now, we saw some very promising results initially, where the longer we illuminated our solution, the more hydroxyl radical production we saw, which was great. However, the more we increased the molecular probe concentration, the more reactive the dust became. This was not ideal for a molecular probe solution, simply because we don't want it to affect the reactivity of the dust. We want it to just be a bystander. Now, we decided to move on to using methanol as a probe. So with hydroxyl radicals, methanol forms formaldehyde, which we then derivatized with a highly absorbing molecule, DNPH, in order to detect it. Now, this method is a very sensitive, very well-characterized technique, which, however, did not work for us simply because of the background production of formaldehyde in our samples. So there are several pathways in which we can form formaldehyde, and we couldn't distinguish those from that formed via hydroxyl radical production. So the last molecular probe we tried was benzene. So with hydroxyl radicals, benzene forms highly fluorescent phenol, which we can quantify that way. This is looking very good so far. We can see that from our calibration curve that we can detect very, very low concentrations, nanomolar concentrations of phenol, which has a linear dependence on our fluorescence, which is great. We also did some preliminary experiments in which we illuminated with our Arizona test dust. And we did manage to see increased production of phenol with time, which we could differentiate from the background production of phenol with time, which was excellent. Now, moving forward, we are looking to use benzene as a molecular probe in this system. Now, the way we're going to start by backtracking on the results we've already seen. So we know that reactivity changes with pH, so we're going to go back and use our benzene to confirm that. We know that reactivity changes with dust size, so we are also going to use benzene to confirm that again also. Thank you so much for listening, and have a great day.